So we're going to discuss gravitational fields, and before we, or as a lead into that, let's just see if we can remember, what is our weight? What is our weight? Any object's weight, ours, whatever, but what is the weight of an object? Well, the weight of an object, and I need you to, if you don't know it already, is the force of gravity on an object. Near or on the Earth's surface, for example, we know that the weight of the object, of any object, is equal to the object's mass times g. So, but based on what we know now about universal gravitation, wait a second, that also means that the force of gravity between us and the Earth, force of gravity between you and Earth, any object, really doesn't have to be you, can also be found using the universal gravitational formula. So, for example, big G, and then what are the two objects involved? All right, well, the mass of the Earth, of course, and the mass of, like I said, we'll just use you as an example, your mass, divided by, I mentioned this in the previous video, what's the distance between you and the Earth? And before you say 0, keep in mind that in this formula, the distances are assumed to be to the centers of the object. So if you're here and you'll be much smaller than that, the distance r involved is from here to you. Well, that is essentially, with the exception of the extra half a meter to your belly button, which is pointless in this case, that is essentially the radius of the Earth. So I'll use capital R since it seems important. So that is the radius of the Earth squared. So this would be the setup if we wanted to find your weight using the concept of universal gravitation. Wait a second, yeah? Now, let's take a second. So here's what I want you to do. Pause the video, make sure you have a calculator, please. It's important. Don't just watch the video without it, go get a calculator. All right, pause the video and go get one. Break out your phone, whatever. So you've got your calculator. Here's what I want to look at. The mass of the Earth is a known quantity. We could look it up. In fact, I'm going to have to here. I'm going to have to in a second. The radius of the Earth is a known quantity, and of course, g is a constant. So what I'm interested in is this force of gravity between you and the Earth. I'm going to lump big G, mass of the Earth, and radius of the Earth squared. I'm going to lump them together and multiply them times your mass, or the mass of whatever object we're discussing. So if you have your phone and you want to Google them real quick, I will attempt to do the same right here. I'm going to try to Google the mass and radius of the Earth. Well, I can look. Usually it's in the cover of physics textbooks, which, you know what, I have one right here. It's probably faster than Google, but it's a knowable number. So let's see what I got. Okay, so the book I'm using, G, of course, capital G. Well, that doesn't work. Let's stick with this. Capital G, of course, is 6.67 times 10 to the negative 11th. Mass of the Earth, according to the textbook I'm looking at here, is 5.98 times 10 to the 24th kilograms, divided by the radius of the Earth in meters. So let's find it. Here it is. 6.38 times 10 to the 6th, but we're going to square that number. So we're going to set it up like that. This is talking about the force of gravity between you and the Earth. Now, here's what I want you to do. I'm not sure if you know how to use, this is also going to be a quick lesson on how to enter these numbers, scientific notation, into your calculator very easily. And in fact, not just very easily, this is the way I would expect you to do this. Because otherwise you're just going to run across all kinds of issues. So let's do this. Let's run through and multiply these two numbers first, shall we? On your calculator, depending on what kind of calculator you have, will be a key that says either EE, two capital E's, or EXP, depending on the type of calculator. For the one that I have in front of you right now, it's this EE right here, which means I have to hit second comma. So that key is important, because when you go to type a number like this, instead of typing times 10 to the negative 6.67 times 10 to the negative 11th, if you use that key, all you have to type in, and I'll write it down here, is actually I'll write it over off to the side, is 6.67, that key, EE, or EXP, depending on your calculator, and then all you have to type in is the exponent, the negative 11 in this case. And you've entered that number. And then in our case, you can hit the times key and do 5.98 EE 24. So let's try that on your calculator. We're going to multiply those two numbers and get the numerator of that. So it's going to be 6.67 second comma. So there's the E, and I'm going to do negative 11 times 5.98 EE 24. And hit enter. And I get an answer of 3.9887 times 10 to the 14th, because on my calculator, I don't know if you can see it or not, but it says 3.988, I rounded a little bit, E14, the capital E there, and some of them some of them don't have an E there, so you have to know how to read this, is the times 10 part. So then the 14 is the exponent. So the numerator over here is going to be 3.9887 times 10 to the 14th. I'm going to divide it by this number squared. Why don't we find that right now? So I'm going to use 6.38 EE 6. And then what I like to do is I hit enter and then I square it. So then I go hit the square key and it will square that. I probably don't have to hit enter, but it just feels safer to me. 0.07 times 10 to the 13th. So I end up with these two numbers, numerator, denominator. And this is the force of gravity equals whatever this number is, don't forget, times your mass or the mass of whatever object we want to find the weight of. Because remember, weight is just another word for force of gravity. So let's finish this thing out. 3.9887 EE 14 divided by 4.07 EE 13. Now, when you do this, I would like to point out that at this point you will know if you've got this right. If you did all this scientific notation stuff right in this last step here, my friends, you'll know. Why will you know? Well, let's hit enter and find out. Oh, look at that. This force of gravity becomes, interesting, 9.8 times your mass or the mass of something else. Well, wait a second. Coincidence? Coincidence? You tell me. Is that a coincidence? No, it's not a coincidence at all. See, if you want to find the force of gravity on something, why would you want to go through and redo this whole part of that equation every single time to get G, when the mass of the Earth and the radius of the Earth aren't going to change, basically? So this part of the gravitational formula is a constant that you can find. And in fact, you could find it for the moon if you knew the mass of the moon and the radius of the moon. You could find it for your mass and your radius. If you treat yourself like a sphere, you even have a little value of G, right? Every object does. You take that value times the mass of some other object, and then you get the force of gravity between you, or the weight. Which leads us to this. This part, the part that I've kind of looped here, that part of the gravitational formula, the capital G, the mass of the, I'm going to say planet, but it doesn't have to be a planet, but it may, but oftentimes it is, divided by the radius of that planet, squared, of course. This right here, which for us boils down to G, is the equation you would use to find the gravitational field on that planet. And so for Earth, a whole nother way of looking at G, other than the acceleration that something will have if you put it into free fall, another whole way of looking at G is the value for the gravitational field on Earth's surface. That 9.8 comes from this constant times the mass of the Earth divided by the radius of the Earth squared. So this is a whole nother way to look at this. So when you have gravitational fields, what that means is it is the newtons, or we'll write it this way. Gravitational field, here we go. G is that. And another way to look at the gravitational field, it is the force per kilogram that you have. So for example, if I want to know an object's weight, the actual force, I need to take the Earth's gravitational field, G, times the mass of the object in question. So this is the field, and this is the object you're placing into that gravitational field. And double check it, but I believe that gravitational field equation, this one, which is just the same as universal gravity but missing that other mass because you don't know what that is also on your equation sheet as an equation you're expected to know how to use. So this idea of G being, another way of looking at G, is the Earth's gravitational field, is an possibly important one as we go forward.